time. Let's do some calculus. Woo woo. Let's do this thing. Okay, so it says we're going to look back at limits. What? Were you expecting this to be a day that we were going back and doing other stuff? Maybe not, but this is your lucky day because we're going to do some limits. This is actually pretty fun. It doesn't quite fit in with the limits unit though, because you don't know how to do derivatives yet. But with derivatives, we have to be careful that we still are following all the derivative rules. You'll see what I mean in a second. So there's some limits that when you directly substitute, that you get some weird forms. That's called the indeterminate form. You might get 0 over 0, or infinity over infinity, or 0 or infinity, or 1 to the infinity. You see all these crazy things? The ones that we're going to focus on the most in this course are these two. The 0 over 0, infinity over infinity. And this could be positive or negative infinity over positive or negative infinity. Doesn't matter which one, the sign doesn't matter. So if you've asked Siri this lately, or if you just have thought about this too much, you can't take 0 divided by 0 or infinity divided by infinity. So you know you have to like factor or do something in order for the limit to exist. That it might be a whole or maybe something else crazy going on in the function. Just because you get an answer like this when you directly substitute does not mean that the limit doesn't exist. And I'm going to show you some examples of that. But we're going to use a new rule that allows us to find the limits even a little bit easier than we did before if you are given a solution in one of these forms. So let's do this thing. This is called L'Hopital's rule. This is not La Hospital. Although if you are having trouble with limits, you might need to go to La Hospital. No, L'Hopital's. Anyway, it's L'Hopital's. There's usually a little tilde over that. I think that's called a tilde. No, tilde's like that. That's in French class. I don't know what that is. But L'Hopital's rule. Assume f of x and g of x are differentiable. Differential means it's also continuous. But it just means that you can take the derivative of both functions. On an open interval containing a such that f of c is equal to g of c is 0. So what that's saying is if I say the limit is x approaches a of f of x over g of x, I get 0 over 0. What this formula, what this theorem, what this rule is saying would be if I take the limit as x approaches a, I can take the derivative of the numerator, derivative of the denominator, and then substitute again. I know, crazy. This is not the quotient rule. I'm not finding the derivative of this entire function. I'm just finding the limit, and this works. So if the limit to the right exists or is infinite, so infinity or negative infinity, so same idea. So if I said the limit as x approaches a, f of x over g of x, and I didn't get 0 over 0, but this time I got infinity over negative infinity or negative infinity over infinity, same thing. I can do this, and this rule is also valid for one-sided limits. So you're like, okay, this 3 minutes of talking, enough already. Let's do this thing. Okay, so the very first thing we want to do, and we always want to do with limits, is substitute. So I'm going to take 2 times 5 squared minus 9 times 5 minus 5 over 5 minus 5. Oh, and I get 0. I'm not even putting equals because I don't want to accidentally write something as equal to 0 over 0 since that's not a number. And the limit still might exist. In the numerator, 5 squared would be 25 times 2 is 50 minus 45 minus 5. Oh, I get 0 again. As soon as you see this, L'Hopital's can be applied. So I'm going to say, so I didn't even write equals anything because this limit isn't equal to 0 over 0. I just got 0 over 0 and now I know L'Hopital's applies. So therefore, L'Hopital's, and you can just write L, H, or if you want to write L'Hopital's, that's okay. L'Hopital's applies or can be applied. This is my justification, and I just want you to get in the habit of doing this just from the first problem. So what I'm going to do is say the limit is x approaches 5. Notation is really important. You have to write down the limit part of this. And now I'm going to take the derivative of the numerator. So this would be 4x minus 9. The derivative of the denominator is 1. And now I can substitute again. So 5. So 4 times 5 is 20. Minus 9 is 11. I can't even substitute here, so I just get 1. My limit, and I can actually set these equal now, is 11. What? Craziness. Okay, let's do another one. So before, if I would substitute a negative 5, I would get 4 minus a negative 5, so plus 5, minus 3 over negative 5 plus 5, which is 0 in the denominator. In the numerator, I would have the square root of 1, which is 1. I didn't, hold on, something happened. Let me see where I was wrong on this. Oh, this is 4 minus a negative 5. This is 9. Silly me. I got this. 4 plus 5 is 9. Square root of 9 is 3 minus 3, which is 0 over 0. So I did all this work. I'm not even putting equals because I don't want to say this limit is equal to 0 over 0. I'm going to say, therefore, L'Hopital's can be applied, or L'Hopital's applies. And so what I want to do is to find this limit. Before, what I would have done is multiplied by the conjugate. I would have multiplied both the numerator and the denominator by the square root of 4 minus x plus 3. And there's a good chance that something would have canceled out. But I want to try L'Hopital's rule on this. So I'm going to take the numerator, which somewhere on the side I'm just going to write 4 minus x to the 1/2 power minus 3. If I take the derivative of that, I would get 1/2 4 minus x to the negative 1/2 power. Don't forget, this is the chain rule because I've got a function within a function. Wow. Let's take the derivative of the inside times negative 1, because that's the derivative of negative x. The derivative of negative 3 is 0. When I rewrite this down here, I'm going to write in the numerator 1 over, negative 1, because this is the negative 1. The 2 would go to the denominator. The 4 minus x to the 1/2 power would go to the denominator. Or I could say this is 4 minus x. Instead of 1/2 power, I'm going to say the root of that. Okay, so this is all the numerator. This was my derivative of my numerator. In the denominator, the derivative is just 1. So I'm showing that L'Hopital's applies. And now I get to substitute in negative 5 again. Negative 1 over 2. 4 minus the negative 5 would be 4 plus 5. 2 times the square root of 9, which is 3. This limit is negative 1/6. Pretty fun, right? You're probably thinking that too. You're thinking, yes, so much fun. Well, in that case, let's do some more. I don't want to stop you from having fun. That'll be not a good thing for me to do. Okay, so let's use this one. So in this one, I've got the limit as x approaches negative infinity. Okay, different on this one, but let's try it. And I've got x squared over e to the negative x. If I take negative infinity squared and I substitute that in, I'm still going to get infinity, because negative infinity times negative infinity would be a positive infinity. Here, this is the same thing as saying e to the negative infinity, be e to the infinity. Any number greater than 1 raised to an infinite power is still going to be infinity. So as soon as I see this happening, infinity over infinity, I can say, oh, therefore L'Hopital's applies. Or can be applied, but that just, I feel like that makes more sense. But also, I just want to write this because it's shorter. So I'm going to write the limit as x approaches negative infinity. And then I take the derivative. So here I'm going to say the derivative of the numerator is 2x. What's the derivative of e to the negative x? E to the anything times the derivative of the anything. Ta-da! Okay, let's try this again. So now I'm going to substitute in negative infinity, and I got 2 times negative infinity would be negative infinity. Down here, I would have e to the negative infinity, so e to the positive infinity times negative 1. What? That's just going to be negative infinity over negative infinity, or positive infinity over positive infinity. Good news. Therefore, L'Hopital's can be applied. So I'm doing it again. And I'm going to say the limit as x approaches negative infinity. You're like, what? I can do this more than once? You can. So I'm going to take the derivative, and now I'm going to do the derivative again. The derivative of 2x is 2. The derivative of e to negative x times negative 1 would be negative, because I'm just carrying along this negative with me. E to negative x times the derivative of the anything, so times the -1, negative, negative, this becomes 2 over e to negative x power. You're like, this doesn't really look all that helpful yet. But do you see how this would become 2 over e to the negative infinity would be e to the infinity. In this, we actually can say, if I take 2 divided by infinity, think about that. I'm taking 2 and I'm dividing it by an infinite number of parts. 2 pretzels divided by an infinite number of people. How much does everyone get? So sad. 0 pretzels. This is the limit. Let's do another one. I knew you were chanting, so I wanted to like join in your excitement and fun. In this one, I'm going to substitute in, and I get -2. And then if you do all this stuff, I'm going to skip ahead, but you can do this to be satisfied. You get 0 over 0. Therefore, L'Hopital's applies. Notice I'm not putting any equal signs in here because this limit actually isn't equal to 0 over 0. I'm going to find an answer in a second. I'm going to say the limit is x approaches -2. And I get 3x squared plus 2x minus 8 over 3x squared plus, what is this, 16x plus 20. By the way, if this were, well, I couldn't do this. If this were the limit as x approaches infinity, I would be looking at the ratio of the coefficients, and I would see this one is, there's a 2 here and a 2 here, and I would have to, and I could find what the horizontal asymptote is like right away, but this is the limit as x approaches -2, so I'm not sure what's happening on the graph there. Okay, so I did all this work, but guess what? If we put in -2, I'm going to say -2 here, -2 here, -2 here, -2 here. You can try this on your own if you don't believe me, but you still get 0 over 0. But there's good news. I feel like I could work on an infomercial. But there's more, Kevin. Yeah, be a good time. There's got to be a better way. There's a Friends episode, but that was really funny. Joey learns how to open a milk carton. Anyway, therefore, L'Hopital's rule applies, and then, so I'm going to do this again. It's like the fun doesn't stop. The derivative of 3x squared plus 2x would be 6x plus 2 over 6x plus 16. Let's try. If we put in -2 this time, 6 times -2 would be -12 plus 2 would be -10. 6 times -2 would be -12 plus 16, which is 4. And I can actually say equals now because this is a real number. If we want to reduce it, we can to -5 over 2. Ta-da! We did it. Let's do another. Oh, trigonometry and transcendental, so like natural log. Okay, let's try this. So we could actually do this an old way too, where because 1 minus cosine of x over x, there's something that we could do, and we could break this up as sine of x over x, 1 minus cosine of x over x. Still the limit is x approaches 0 of both parts, and we still could do this. So if you wanted to, this is the old way. But the new way, limit is x approaches 0, if I substitute this in, and I get sine of 0, 1 minus cosine of 0 over 0 squared. Sine of 0 is still 0. So 0 times anything, but this is going to be 0 times 0 over 0. So this is definitely 0 over 0. So I'm going to say, therefore, L'Hopital's applies. And I'm going to do the same thing as before, but limit as x approaches 0. And in this one, yeah, I'm actually still going to split this up a little bit, because right now, if I did this, I would have to take the product rule, and this is going to get really, really messy. So why don't I split it up? Sine of x over x. Limit is x approaches 0. And I get 1 minus cosine of x over x. And you're like, Miss DeWald, that was the old way. Why would that help me? Because I know we memorized some not derivatives, we memorized these limits, and I knew that this was 1 and this was 0, and I can multiply them and whatever. I'm still going to use L'Hopital's rule, because do you see how this part is going to be 0 over 0 if I substitute in? This would be 0 over 0. So L'Hopital's applies in each one of these individual fractions still. So even if you didn't remember these, because you probably memorized them for the test and then moved on, you only have so much space in your head. And while I think calculus should take up like 99% of it, I'm guessing that it doesn't most days. In my head either. Actually, it takes up a lot of space in my head too. Okay, limit as x approaches 0. The derivative of sine of x is cosine of x. The derivative of x is 1. Over here, I'm going to do the same thing. The derivative of 1 is 0. The derivative of negative cosine is positive sine of x over 1. And now we can substitute. Limit as x approaches 0 of cosine. Cosine, when I think about this, I think about the cosine curve. At 0, I get 1 times sine curve at 0 is 0. 1 times 0 is 0. So it's kind of taking something that we did before and learning how to separate fractions and then combining it with L'Hopital's rule to make it the easiest that we possibly can. Okay, let's try this one. Limit as x approaches 1. The first thing is, if you take the natural log of 1, you should know that one. If you don't, now is a good time to learn it. The natural log of 1 is just 0. Minus 1 plus 1 is going to be 0. I almost wrote an equal sign. E to the first power minus e, that's just like saying 3 minus 3, or 3 to the first power minus 3, you get 0. E minus e is still 0. Okay, so because of that, therefore, L'Hopital's applies. I'm going to take the limit as x approaches 1. The natural log of x, the derivative of natural log of x is 1 over x minus 1. The derivative of 1 is just 0. The derivative of e to the anything is e to the anything times the derivative of the anything, which in this case is just 1. This number, negative e, is just a number. So like if I ask you what the derivative of 1 was, we just said 0. So the derivative of negative e is just 0. So even though I left a lot of room out here, this is just the derivative. Now I'm going to try substituting. So I can see that I get 1 over 1, which would be 1, minus 1, which is 0. But I put an equal sign. I kind of jumped ahead of myself because e to the first power is just e. So I have 0 divided by e. 0 divided by e, 0 divided by anything is still 0. Ta-da! I can make this look like a little camera. Are you ready? Isn't that fun? Okay, but now I'm going to put it back. Next. Limit as x approaches infinity. So let's do this one. So if I substitute in, just because I know this one, I'm taking infinity to the third power plus infinity squared minus 3 times infinity. I'm actually going to get infinity. In the denominator, this says, this is super little, so if you don't have these notes beside you, this is going to be hard to see. 4x to the third minus 6 would be infinity also. Infinity over infinity, therefore L'Hopital's applies, and I'm going to take the derivative. Limit as x approaches infinity. This would be 9x squared plus 10x minus 3. 12x squared. And then that's it. And then I'm going to substitute in. Infinity squared times 9 plus 10 times infinity. Oh my goodness, that's really big. I get infinity. 12 times infinity squared is infinity again. L'Hopital's applies. It's like the grown-up version of This Is a Song That Doesn't End, except it sometimes ends in a minute, and we'll see that, but you know. So if you want that song stuck in your head right now, you can think about it. It's a song that never ends. Yes, it goes on and on, my friend. Some people started singing it, not knowing what it was. Though continues. Okay, anyway, I'm going to stop. Just like this is eventually going to stop. L'Hopital's apply, so I'm going to say the limit is x approaches infinity. Make sure that you have this notation too. 18x plus 10 over 24x. Oh, still going to get infinity over infinity when I substitute. Therefore, L'Hopital's applies. One more time. We're so close. Limit as x approaches infinity. This would be 18 over 24. 18 over 24 reduces to 3/4. I had to check myself there to make sure. Yeah, divided by 6, divided by 6. We're good. We did it. This one, because I have limit as x approaches infinity, you're thinking about end behavior, horizontal asymptotes. And so I could have just said 3/4 since my degree in the numerator and degree in the denominator were both 3. Super hard to see on the video, but they're just 3. Let's do one more. In this one, if I substitute 4 times x squared, 4 times infinity squared minus 3 times infinity, still going to be infinity. This is a huge number. E to 2 times infinity plus ln of e, still going to be a huge number, so we get infinity. Therefore, L'Hopital applies, or can be applied, either one. Limit as x approaches infinity, take the derivative of the numerator, e to x minus 3. In the denominator, the derivative of e to the anything is e to the anything times the derivative of the anything. The derivative of natural log of x is 1 over the anything times the derivative of the anything. Derivative of x in this case is just 1. So now if I substitute infinity, I would get infinity over infinity plus 1 over infinity would be 0. This is still infinity over infinity. Therefore, L'Hopital applies. Limit as x approaches infinity, take the derivative again. 8. In the denominator, you would get 2e to the 2x, because e to the anything. And so the 2 just stays along for the ride. The e to the 2x is e to the anything times the derivative of the anything. Plus, instead of taking 1 over x, I'm going to rewrite this on the side as x to the negative first. Take the derivative, you would get negative x to the negative second power. And so if I rewrote that over here, I would say minus 1 over x to the second power. If I substitute in 8, that's funny, it's right here. If I substitute in infinity, I get 8 still, because that wouldn't change, over 2e to the 2x times 2. So 4 times e to the 2 times 2 to the infinity, that doesn't make any sense. 2 times infinity would still be infinity. E to the infinity power would be infinity times 4, still infinity. Minus, this would still be 0 for this limit. 8 over infinity. What number is that? 0. It's like if you ate cookies divided by an infinite number of people. A waste of cookies because no one gets any. Okay, we did it. Thanks for being you. Thanks for being awesome. And if you've reached your limit, that's okay because we're done for today. Okay, I'll talk to you later. Thank you so much for doing this. You're awesome. Bye.